I'm Ondřej. So I came here from the Czech Republic, and here you can see some things which I like. I like doing weird stuff with JavaScript. I like playing text mode roguelike games, and I do like maths. Do you like maths? Yeah, of course you do, because we're all friends here, right? So let's start with a short quiz. Do you guess this person? Well, this is a lightning talk, so we're out of time. Sorry, no more quizzes. This is Alan Turing. He was very well-known mathematician, logician, crypto analyst. This guy was doing crypto even before Bitcoin, so he's like the OG crypto guy. And he also happened to write an article called On Computable Numbers back in 1936, where he introduced the concept of a Turing machine. And we're fortunate to have one Turing machine here right now. So this, what you're looking at, is a Turing machine. And this machine, what does it do? I don't have my cursor. Here it is. So this is the head of the machine. It's red. It's a robot. And this machine has a list of light bulbs. This is called the tape. This is the memory of the machine. And this list is full of light bulbs, and they're all turned off. So we can run this machine, but this machine wouldn't work without a set of instructions. And the table below the machines, these are those instructions. And they say, well, if you're a red robot right now and you're standing next to a light bulb which is turned off, then what should we do? We shall leave the light bulb off, move to the right, and remain in the red state so we can run this machine. And you can see that it's still moving, right? And it goes on and on and on. And it's basically doing nothing interesting. So we can do better. We can adjust the rules for this Turing machine, and we can say, well, if you are standing next to a light bulb that's powered off, let's turn it on and move to the right. So now the same machine has a slightly different instruction set, and is turning all the light bulbs which are there, it's turning them on, and moves and moves and moves and moves. And the problem now is that the machine itself has no notion of ending the job. It's non-terminating, it's not halting. So we can improve on that, and we could modify the rule set. So instead of remaining in the red state, the machine may, after moving to the right, turn into black, the halting state, which means the work is done. So let's try this again, how this works. Nope, not good. Let's reload this. Yep. Great. Turn one light bulb on, move right, and die. And that's all we can do. But that's not really exciting, is it? So to improve this, we move into two colors. We now have the robot, which can be red or green. So we have two states, and we have many more instructions possible because the robot now has 4 options, 4 states, when combined with the symbols on the tape. So this set of instructions will move, turn the light bulbs on, and then halt. And the result of this machine with 2 states, is 4 light bulbs that have been turned on the tape. And this brings us to the topic of the talk, the Busy Beaver game. So for a given number of states, find a Turing machine that writes the maximum number of ones on an initially blank tape before halting. This is an original formulation by the Hungarian mathematician Tibor Radó back in 1962. And this game keeps mathematicians busy ever since. How? Well, because finding busy beavers, these Turing machines, is very hard for 2 reasons. The reason number 1, there are a large amount of those. Because you can create a large number of Turing machines for a given set of states, because they are defined by their function, by their table, and there are many combinations. And the second reason is because it's hard to find whether a machine halts or not. This is the famous halting problem. So what are the results so far? For 1 state, we know that we are able to turn on 1 light bulb. For 2, 4. For 3 states, 6. Not much of an improvement. And for 4 states, the best result is 13. So what do you think is the best value for a 5-color Turing machine? And now this is a trick question. If you asked me 2 years ago, I would say that we do not know, because this result has only been proven the last year, and it's 4098, proven in 2024. But you know these mathematicians, they like to go forward, right? So they're asking what is the best result for a 6-state Turing machine. And we don't know. Back in 2010, Pavel Kropitz, Slovak, studying at Czech Charles University in Prague, proved that there are more than 10 to the power of 18,000 score for a Turing machine with 6 states. And then he improved that using this extreme notation for big numbers. And it was further improved this year using this extreme number notation. And if you think about these numbers, your head will go boom. And we don't have time for that, so here are some links if you're interested. Thank you for your time.
Thank you so much.
Woo!